this is our Honors Chemistry section 15.2 lesson video. Since this section is a little long, I am going to break it up into two parts. So we're going to talk about homogeneous aqueous systems. So an aqueous solution is water that contains dissolved substances. So like salt water, sweet tea, those are aqueous systems. So in a solution, the dissolving medium is the solvent and the dissolved particles are the solute. So the easiest way to remember it is a solvent dissolves a solute. So like in Kool-Aid, it makes sense to say the water dissolves the Kool-Aid powder or the water dissolves the sugar because the solvent is water and the solutes are the Kool-Aid powder and the sugar. It doesn't make any sense to say the Kool-Aid powder dissolves the water. So that's how you can tell which is which. In an aqueous system, of course, the solvent, though, is going to be water. So how do these substances dissolve in water? Well, this is how an ionic compound dissolves in water. It says individual solute ions break away from a crystal, the negatively and positively charged ions become surrounded by solvent molecules, and the ionic crystal dissolves. This process, called solvation, helps stabilize the ions in solution and prevents the cations and anions from recombining. So what happens is you have your cations and anions in your ionic compound, and the water molecules, you need to remember that oxygen is partially negative and your hydrogens are partially positive. If an oxygen bumps into one of those positive cations, it's going to be attracted to it. So that positive cation will kind of separate and dissolve from the crystal, and then water molecules are going to surround it with their oxygen side facing the cation because, of course, opposites attract. So that partial negative oxygen will be attracted to that positive cation. And so once that ion is surrounded, it's not going to want to reattach to the crystal because it can't attract to a negative anion at that point because it's surrounded by the water molecules. They kind of provide like a buffer. And then the opposite happens to the anions. When the positive hydrogen side, remember they're partially positive, bumps into the anion, it becomes attracted to the anion because the hydrogens are partially positive and the anion is negative. And so again, what happens is the water molecules surround the anion, but because anions are negative, it's the hydrogen side of the water molecules that are attracted to it. And then again, once they surround that anion, it's not free to go back and reattach to the crystal. So solvation is the interaction between the solute and solvent particles, like I just showed you in the previous slide. Hydration is the interaction between the solute and solvent particles when the solvent is water. So hydration is just a specific form of solvation where the solvent is water, so in an aqueous system. So delta H is just our change in enthalpy, which is related to heat and energy. And so our delta H, or our change in enthalpy when you make a solution, involves three different energy changes. So what's happening in each of these? So delta H of solution is the energy change when the solution forms. So of course it could be positive, implying it's absorbing energy, or it could be negative, implying it's releasing energy. So delta H sub 1 is the energy required to separate the solute particles. So since it's energy required, that's an endothermic process because the solute particles are attracted to one another. And so to pull them apart requires energy. Delta H2 is the energy required to separate the solvent particles. Because remember, water forms hydrogen bonding with each other. So we have to break apart that hydrogen bonding in order for the solute and solvent to interact. And so again, since this is required, this is an endothermic process. So we would have a positive value for this one and a positive value for that one because they're both endothermic. Now delta H3 is the energy released when the solute and solvent particles attract one another. So now we have new attractions forming, which is favorable. So energy is released, and this number should be exothermic, which means it would be negative. So depending on the actual values of the two positives and the negative, that will determine whether energy is overall released or absorbed when the solution forms. So here again you can see an endothermic process is separating the solvent. Separating the solute is also an endothermic process. But then when the solute and solvent can form attractions with each other, that is an exothermic process where energy is released. So how do we know if a solution is going to form? Because not all the time will a substance dissolve in something else. So processes that are exothermic tend to be spontaneous, but endothermic processes still occur. An example, ammonium nitrate will spontaneously dissolve in water even though its delta H of solution is a positive 26.4, implying that it needs energy to do that, which is not normally a spontaneous process. So why does this happen? Well, spontaneous processes involve two factors. Energy, we want to be endothermic. Energy, we want to be exothermic. However, it also is based on the tendency to spread out. Okay, so when we're talking about whether or not something is spontaneous, it is based on energy, which is what we just talked about, the delta H of solution, and spontaneous processes tend to be exothermic. But we have to take into account this other part, the tendency to spread out. So entropy is the degree of randomness or disorder of a system. So the more entropy, the more randomness or disorder that we have. Processes in which the entropy or randomness of the components increases tend to be spontaneous. So we want to release energy and be exothermic to be spontaneous, and we want to increase our randomness or disorder. So the formation of solutions involves enthalpy, which is energy change, and entropy, which is randomness. Okay, so we start with a solid that is very orderly, and when we dissolve it in water, it becomes random and spread out, and it loses that orderliness, so it becomes disordered. And so that's what allows some solutions to form, even if they have a positive delta H. So, first sample exercise. It says the picture below shows the following reaction. So we have a solid, and we have gaseous water or water vapor, and it's forming this solid. It says it's a hydrate. That's why we have the water attached to it. It says essentially all of the water vapor in the closed container is consumed in this reaction. So we can see here we have a solid and we have some gas particles around. The gas happens to be water vapor. And then once it's allowed to react, it all comes together as one solid. So our question says, if we consider our system to consist initially of our solid and our water vapor, does the system become more or less ordered in the process? Well, let's look back at our picture. Here I have gas particles everywhere, all spread out, and then I have this orderly solid in the middle. Here, everything is an orderly solid, so everything's orderly at that point. So the process becomes more ordered because that gas, all the randomness of those gas particles, is now orderly when it's in its hydrate form. Does the entropy of the system increase or decrease? Well, remember, entropy is based on disorder. So we're becoming more ordered, so our entropy would, in that case, decrease. Our entropy would decrease. All right, so let's look at another one. Maybe you can pause it and you can try this one on your own. So it says, does the entropy of a system increase or decrease when the stopcock is opened to allow the mixing of the two gases in the apparatus? So here, this is closed, and so we just have nitrogen gas on this side, we just have oxygen gas on this side. So what they're saying is we're going to open the stopcock and allow the two gases to mix. So what would happen to the entropy? So pause it, try it, I'll assume you've done that. So once we allow the two gases to mix, now it's not as orderly. It's orderly right now. I have nitrogen on this side, I have oxygen on this side. Once I allow it to mix, that increases the randomness. So your entropy would increase. Your entropy would increase. So hopefully you got that right. All right, so the ability of substances to form solutions depends on two factors. The intermolecular forces involved, because of course we are breaking some forces and making new ones, and the tendency of the substance to spread out into larger volumes. So that's where our entropy comes in. So let's quickly review kind of our intermolecular forces, and this time we're finally going to focus on the ion-dipole. So ion-dipole forces are present when ionic substances dissolve in water. So when an ionic compound dissolves in water, we might have a cation, which has a full positive charge, and then our water molecules, remember, the oxygen portion of it is going to be attracted because the oxygen is partially negative. So water, because the hydrogens, of course, are partially positive. So water has a dipole moment, so so of course that's the dipole portion, but it's not being attracted to another water molecule with another dipole moment. Now it's being attracted to an ion, so that's where ion-dipole comes. So you have an actual ion and you have a molecule with a dipole moment. Dispersion forces are present when nonpolar substances form solutions. Remember, dispersion forces are present in all of them, London dispersion. And solutions form when the attractive forces between the solute and solvent are comparable to the forces that exist between two solute or two solvent particles. So remember, we're having to break apart the solute, we're having to break apart the solvent, both require energy, and then we're releasing energy when we form a solute-solvent attraction. And so we need the forces to be comparable. If the solutes have too many forces, then we might not be able to pull them apart to let the water surround it. So there is a rule of thumb that we can follow. So as a rule, polar solvents such as water will dissolve polar solutes such as ethanol. They will also dissolve a lot of ionic compounds. So polar will dissolve polar and ionic. As a rule, nonpolar solvents such as gasoline dissolve nonpolar solutes such as oil. Because, again, nonpolar and nonpolar both only experience London dispersion forces. Whereas polar and polar, they would have London dispersion, they would have dipole-dipole, they could have hydrogen bonding. This relationship can be summed up by the expression like dissolves like. So the more similar the intermolecular forces are, the more likely a solvent will dissolve a solute.